The Force of Gravitation by Michael Faraday. Let me now give you another illustration of this power. You know what a pendulum is. I have one here, figure 1, and if I set it swinging, it will continue to swing to and fro. Now I wonder whether you can tell me why that body oscillates to and fro, that pendulum bob, as it is sometimes called. Observe, if I hold the straight stick horizontally, as high as the position of the ball at the two ends of its journey, you see that the ball is in a higher position at the two extremities than it is when in the middle. Starting from one end of the stick, the ball falls toward the center, and then rising again to the opposite end, it constantly tries to fall to the lowest point, swinging and vibrating most beautifully, and with wonderful properties in other respects, the time of its vibration, and so on, but concerning which we will not now trouble ourselves. If a gold leaf, or piece of thread, or any other substance were hung where this ball is, it would swing to and fro in the same manner, and in the same time too. Do not be startled at this statement. I repeat, in the same manner, and in the same time, and you will see by and by how this is. Now that power which caused the water to descend in the balance, which made the iron weight press upon and flatten the bubble of air which caused the swinging to and fro of the pendulum, that power is entirely due to the attraction which there is between the falling body and the earth. Let us be slow and careful to comprehend this. It is not that the earth has any particular attraction toward bodies which fall to it, but that all these bodies possess an attraction every one toward the other. It is not that the earth has any special power which these balls themselves have not, for just as much power as the earth has to attract these two balls, dropping two ivory balls, just so much power have they in proportion to their bulks to draw themselves one to the other, and the only reason why they fall so quickly to the earth is owing to its greater size. Now if I were to place these two balls near together, I should not be able, by the most delicate arrangement of apparatus, to make you, or myself, sensible that these balls did attract one another, and yet we know that such is the case, because if, instead of taking a small ivory ball, we take a mountain, and put a ball like this near it, we find that, owing to the vast size of the mountain as compared with the billiard ball, the latter is drawn slightly toward it, showing clearly that an attraction does exist, just as it did between the shellac which I rubbed and the piece of paper which was overturned by it. Now it is not very easy to make these things quite clear at the outset, and I must take care not to leave anything unexplained as I proceed, and, therefore, I must make you clearly understand that all bodies are attracted to the earth, or, to use a more learned term, gravitate. You will not mind my using this word, for when I say that this penny piece gravitates, I mean nothing more nor less than that it falls toward the earth, and, if not intercepted, it would go on falling, until it arrived at what we call the center of gravity of the earth, which I will explain to you by and by. I want you to understand that this property of gravitation is never lost, that every substance possesses it, that there is never any change in the quantity of it, and, first of all, I will take as illustration a piece of marble. Now this marble has weight, as you will see if I put it in these scales. It weighs the balance down, and if I take it off, the balance goes back again and resumes its equilibrium. I can decompose this marble and change it in the same manner as I can change ice into water and water into steam. I can convert a part of it into its own steam easily, and show you that this steam from the marble has the property of remaining in the same place at common temperatures, which water steam has not. If I add a little liquid to the marble and decompose it, footnote 6, marble is composed of carbonic acid and lime, and, in chemical language, is called carbonate of lime. When sulfuric acid is added to it, the carbonic acid is set free, and the sulfuric acid unites with the lime to form sulfate of lime. End of footnote. I get that which you see. The lecturer here put several lumps of marble into a glass jar, and poured water, and then acid over them. The carbonic acid immediately commenced to escape with considerable effervescence, the appearance of boiling, which is only the separation of one part of the marble from another. Now this marble steam and that water steam, and all other steams, gravitate just like any other substance does. They all are attracted the one toward the other, and all fall toward the earth, and what I want you to see is that this steam gravitates. I have here, figure 2, a large vessel placed upon a balance, and the moment I pour this steam into it you see that the steam gravitates. Just watch the index, and see whether it tilts over or not. The lecturer here poured the carbonic acid out of the glass in which it was being generated into the vessel suspended on the balance, when the gravitation of the carbonic acid was at once apparent. Look how it is going down. How pretty that is. I poured nothing in but the invisible steam or vapor, or gas which came from the marble, but you see that part of the marble, although it has taken the shape of air, still gravitates as it did before. Now will it weigh down that bit of paper? Placing a piece of paper in the opposite scale. Yes, more than that, it nearly weighs down this bit of paper, placing another piece of paper in. And thus you see that other forms of matter besides solids and liquids tend to fall to the earth, and, therefore, you will accept from me the fact that all things gravitate, whatever may be their form or condition. Now here is another chemical test which is very readily applied. Some of the carbonic acid was poured from one vessel into another, and its presence in the latter shown by introducing into it a lighted taper, which was immediately extinguished. You see from this result also that it gravitates. All these experiments show you that, tried by the balance, tried by pouring like water from one vessel to another, this steam or vapor or gas is, like all other things, attracted to the earth. Carbonic acid, under ordinary circumstances, is a colorless invisible gas, about half as heavy again as air. Dr. Faraday first showed that under great pressure it could be obtained in a liquid state. Filleurier, a French chemist, afterward found that it could be solidified. There is another point I want in the next place to draw your attention to. I have here a quantity of shot, each of these falls separately, and each has its own gravitating power, as you perceive when I let them fall loosely on a sheet of paper. If I put them into a bottle, I collect them together as one mass, and philosophers have discovered that there is a certain point in the middle of the whole collection of shots that may be considered as the one point in which all their gravitating power is centered, and that point they call the center of gravity. It is not at all a bad name, and rather a short one, the center of gravity. Now suppose I take a sheet of pasteboard, or any other thing easily dealt with, and run a bradawl through it at one corner, point A, figure 3, and Mr. Anderson holds that up in his hand before us, and I then take a piece of thread, and an ivory ball, and hang that upon the awl, then the center of gravity of both the pasteboard and the ball and string are as near as they can get to the center of the earth, that is to say, the whole of the attracting power of the earth is, as it were, centered in a single point of the cardboard, and this point is exactly below the point of suspension. All I have to do, therefore, is to draw a line, AB, corresponding with the string, and we shall find that the center of gravity is somewhere in that line. But where? To find that out, all we have to do is to take another place for the awl, figure 4, hang the plumb line, and make the same experiment, and there, at the point C, is the center of gravity. There were the two lines which I have traced cross each other, and if I take that pasteboard and make a hole with the bradawl through it at that point, you will see it will be supported in any position in which it may be placed. Now, knowing that, what do I do when I try to stand upon one leg? Do you not see that I push myself over to the left side, and quietly take up the right leg, and thus bring some central point in my body over this left leg? What is that point which I throw over? You will know at once that it is the center of gravity, that point in me where the whole gravitating force of my body is centered, and which I thus bring in a line over my foot. Here is a toy I happened to see the other day, which will, I think, serve to illustrate our subject very well. That toy ought to lie something in this manner, figure 5, and would do so if it were uniform in substance, but you see it does not, it will get up again. And now philosophy comes to our aid, and I am perfectly sure, without looking inside the figure, that there is some arrangement by which the center of gravity is at the lowest point when the image is standing upright, and we may be certain, when I am tilting it over, see figure 6, that I am lifting up the center of gravity, A, and raising it from the earth. All this is effected by putting a piece of lead inside the lower part of the image, and making the base of large curvature, and there you have the whole secret. But what will happen if I try to make the figure stand upon a sharp point? You observe I must get that point exactly under the center of gravity, or it will fall over thus, endeavoring unsuccessfully to balance it, and this, you see, is a difficult matter. I cannot make it stand steadily, but if I embarrass this poor old lady with a world of trouble, and hang this wire with bullets at each end about her neck, it is very evident that, owing to there being those balls of lead hanging down on either side, in addition to the lead inside, I have lowered the center of gravity, and now she will stand upon this point, figure 7, and, what is more, she proves the truth of our philosophy by standing sideways. I remember an experiment which puzzled me very much when a boy. I read it in a conjuring book, and this was how the problem was put to us: how, as the book said, how to hang a pail of water, by means of a stick, upon the side of a table, figure 8. Now I have here a table, a piece of stick, and a pail, and the proposition is, how can that pail be hung to the edge of this table? It is to be done, and can you at all anticipate what arrangement I shall make to enable me to succeed? Why this. I take a stick, and put it in the pail between the bottom and the horizontal piece of wood, and thus give it a stiff handle, and there it is, and, what is more, the more water I put into the pail, the better it will hang. It is very true that before I quite succeeded I had the misfortune to push the bottoms of several pails out, but here it is hanging firmly, figure 9, and you now see how you can hang up the pail in the way which the conjuring books require. Again, if you are really so inclined, and I do hope all of you are, you will find a great deal of philosophy in this, holding up a cork and a pointed thin stick about a foot long. Do not refer to your toy books, and say you have seen that before. Answer me rather, if I ask, have you understood it before? It is an experiment which appeared very wonderful to me when I was a boy. I used to take a piece of cork, and I remember I thought at first that it was very important that it should be cut out in the shape of man, but by degrees I got rid of that idea, and the problem was to balance it on the point of a stick. Now you will see I have only to place 2 sharp-pointed sticks one each side, and give it wings, thus, and you will find this beautiful condition fulfilled. We come now to another point. All bodies, whether heavy or light, fall to the earth by this force which we call gravity. By observation, moreover, we see that bodies do not occupy the same time in falling. I think you will be able to see that this piece of paper and that ivory ball fall with different velocities to the table, dropping them, and if, again, I take a feather and an ivory ball, and let them fall, you see they reach the table or earth at different times, that is to say, the ball falls faster than the feather. Now that should not be so, for all bodies do fall equally fast to the earth. There are 1 or 2 beautiful points included in that statement. First of all, it is manifest that an ounce, or a pound, or a ton, or 1,000 tons, all fall equally fast, no one faster than another. Here are 2 balls of lead, a very light one and a very heavy one, and you perceive they both fall to the earth in the same time. Now if I were to put into a little bag a number of these balls sufficient to make up a bulk equal to the large one, they would also fall in the same time, for it an avalanche fall from the mountains, the rocks, snow and ice, together falling toward the earth, fall with the same velocity, whatever be their size. I cannot take a better illustration of this than of gold leaf, because it brings before us the reason of this apparent difference in the time of the fall. Here is a piece of gold leaf. Now if I take a lump of gold and this gold leaf, and let them fall through the air together, you see that the lump of gold, the sovereign or coin, will fall much faster than the gold leaf. But why? They are both gold, whether sovereign or gold leaf. Why should they not fall to the earth with the same quickness? They would do so, but that the air around our globe interferes very much where we have the piece of gold so extended and enlarged as to offer much obstruction on falling through it. It will, however, show you that gold leaf does fall as fast when the resistance of the air is excluded, for if I take a piece of gold leaf and hang it in the center of a bottle so that the gold, and the bottle, and the air within shall all have an equal chance of falling, then the gold leaf will fall as fast as anything else. And if I suspend the bottle containing the gold leaf to a string, and set it oscillating like a pendulum, I may make it vibrate as hard as I please and the gold leaf will not be disturbed, but will swing as steadily as a piece of iron would do, and I might even swing it round my head with any degree of force, and it would remain undisturbed. Or I can try another kind of experiment. If I raise the gold leaf in this way, pulling the bottle up to the ceiling of the theater by means of a cord and pulley, and then suddenly letting it fall within a few inches of the lecture table, and allow it then to fall from the ceiling downward, I will put something beneath to catch it. Supposing I should be maladroit, you will perceive that the gold leaf is not in the least disturbed. The resistance of the air having been avoided, the glass bottle and gold leaf all fall exactly in the same time. We have now pumped the air out of the vessel, and you will perceive that the gold leaf will fall as quickly in this vacuum as the coin does in the air. I am now going to let it loose, and you must watch to see how rapidly it falls. There. Letting the gold loose. There it is, falling as gold should fall. I am sorry to see our time for parting is drawing so near. As we proceed, I intend to write upon the board behind me certain words, so as to recall to your minds what we have already examined, and I put the word forces as a heading, and I will then add beneath the names of the special forces according to the order in which we consider them, and although I fear that I have not sufficiently pointed out to you the more important circumstances connected with the force of gravitation, especially the law which governs its attraction, for which I think I must take up a little time at our next meeting, still I will put that word on the board, and hope you will now remember that we have in some degree considered the force of gravitation, that force which causes all bodies to attract each other when they are at sensible distances apart, and tends to draw them together.